So I left you on a little bit of a cliffhanger on that last video. I said, if the claim was more than 35% and the sample shows 36%, why didn't we support the claim? Because last I checked, 36% is bigger than 35%. So what gives? Like, I don't understand what's happening here. Well, if it was that simple to look at this and go, oh, 36 is bigger than 35, we'd be done. Like, why did we go through all of this if we could have just compared those two numbers? So see, there's something deeper going on here than just, oh yeah, 36 is bigger than 35. It is bigger. Yes, I agree. It's bigger. Here's the kicker. It's not significantly bigger. And what we're testing is statistical significance. Your results have to be significantly bigger. Well, what is significantly bigger? Like 37% or 40%? Well, I can't answer that question. It depends on the math. The math will tell you what is significantly bigger because it depends on a lot of things. It depends on alpha. It depends on the sample size. It depends on a lot of things. One other thing that I want to make clear that I don't know if I made it 100% clear in the last video, so I want to make sure that you understand. What is this p-value? When the calculator drew this picture, it sure looks like what we have, but it's not. It's not the same thing. So let me explain to you what this p-value of 0.0515 actually is. This blue shaded region on the calculator is showing 5%. My not to scale picture, this is 1%. This blue is actually showing you the probability from my pink test statistic over. From here all the way over. So if I were to shade all the way out, that's 5%. That's what this is showing. And from the test statistic shaded out is bigger than my little shaded region. And when their shaded region is bigger than our shaded region, that means the p-value is bigger than alpha. So you can't just copy down what the calculator shows and assume that it's going to be the same. And we'll see that some more in some other problems. But I just wanted to point out that this shaded is not the same thing as this. Okay? All right. Also, alpha, it's the level of significance. It's the level by which significance is determined. Your results are only significant if you're less than alpha. Our p-value was not less than alpha. We did not have statistically significant results. This is the cutoff for significance. And it changes from problem to problem. So let's try some more, because I think the more of these we do, the more you guys will understand it. This one says, in the year 2000, 58% of females aged 15 or older lived alone, according to the U.S. Census Bureau. So the census was done in 2000, and now here we are in 2020. We're doing it again. So it's every 10 years, I think. A sociologist tests whether the percentage is different today by conducting a random sample of 500 females, aged 15 or older, and finds that 285 are living alone, based on the study that they did. Is there sufficient evidence at alpha equals 0.10 to conclude that the proportion has changed since 2000? All right, let's talk about the numbers that are not important in this problem. The age 15 years, that's not important. Also, the year is not really important. That 2000 is not a number that I'm going to use for any calculations. So I'm going to mark those off. Okay. The numbers I have a 285. I have a 500. They told me alpha. So I need to try to figure out what is my claim, what is X, and what is N. Okay. So let's see. What are they claiming? Or what is she testing? Whether the percentage is different today or that the proportion has changed. What does changed mean? Well, changed is a very non-committal word. The sociologist is not saying, well, they think it's bigger now or that they think it's smaller. They're just saying they think it's different. So when you see words like different and changed, it means not equals. Not equal to what? Not equal to what it was back in 2000, which was 58%. So again, you got to convert it over to a decimal. So the sociologist is claiming that the proportion is no longer 0.58. Of these two numbers, the bigger one is always N. So They sampled 500 females, found out 285 were living alone. I am not going to check the requirements on this one, but you would take n times 0.58 times the complement of 0.58, and you'd want to make sure that it's bigger than 10, but it is. So I'm not going to check it here. All right, so for HO, you always put in equals. That's HO. The claim goes here. This is our claim. And what type of a tailed test would this be? When you have a not equal sign, that makes a two-tailed test. And because it's a two-tailed test, I can tell you we're going to get two critical values. So I'm going to go ahead and put the plus and minus there because I know it's going to have two critical values. The alpha they told us to use was 0.10. Okay, so now what do? You go to your table. Here's the table. Our alpha was 0.10. We have a two-tailed test. See the plus and minus? It's there. 1.645. 1.645. And I'm going to go ahead and immediately draw my picture so I don't forget. Try to make it look symmetric if you can. All right, now 1.645 is not way down in the tail, it's kind of about here. Please label underneath. So there's one of the rejection regions. The other one's on the other side, and I'll explain to you why we need two. We need two rejection regions. We have to have one weighting on both sides because they were non-committal. They said not 0.58. Well, what if it ends up bigger? Or what if it ends up smaller? Well, we have to be ready and waiting on both sides. We're like ready to catch that test statistic wherever it might fall. You have to be ready and waiting on both ends. So that's what two-tailed tests do. They give you half of alpha here and half of alpha here. So if alpha is 10, then this side would be 5%, and this side would also be 5%. And so you have 10% total rejection area. All right, now we're going to go to the calculator. Stat, tests, number 5. This time the number in our HO is 0.58. 285 out of 500. And I have to hit enter to move my highlighting over. You don't want it to just be blinking there. You need it to be like solid highlighting there. Okay, so not equals, because that's what our claim has. And I think I'm just going to go to draw. Let's just go to draw and see what it does. And don't try to reproduce what the calculator is showing. See, they have a lot more shading than what we have. And I can tell you this, guys, when you see the calculator start shading a whole bunch of stuff, that doesn't look good for your claim. We're hoping the calculator doesn't shade much at all. Here's the test statistic, negative 0.45. Here's the p-value, 0.6505. So we're going to copy those down. Negative 0.45 and 0.6505. That's what the calculator told me. You can also go to the calculate screen, and I'm going to go there because I want to look at something in there. I want to see p-hat. See, it tells us there's the test statistic, here's the p-value, they're just not rounded, there's p-hat. I really kind of want to know that number, just for the sake of argument. It was 0.57. Now, I could have found it myself if I wanted to. I could have divided those and gotten that number, but I might as well let the calculator do it. You paid enough for the calculator, let it do some work for you. All right, so she claimed it is not 0.58. And our sample shows it's not, it's 0.57, right? But is that different enough? That's what we want to know. So let's put this test statistic on the picture. So it's negative. We have to draw it on the left side. It has to be over here. The question is it in the white or the purple? Here's 0. Here's negative 1.645. So where would negative 0.45 fall? I don't know, about like right here maybe? But it's definitely not in the rejection region. We cannot reject HO. Let's look at this one. Now this is a pretty big alpha, 10%. Remember, that talks about how willing you are to live with the fact you might make a type 1 error. So how does 6505 compare to 10? Well, it's way bigger. And it's not just a little bit bigger, y'all. This is like way, way, way bigger. And so that also tells us do not reject. So we have two things telling us the same story. This picture that was drawn, if I go back here to draw and let it draw again, that, what it's shading there in blue, that is from the test statistic over and then doubled. Why did they double it? Because it's a two-tailed test. So all of that blue is the 6505. Okay, it's way bigger. It's bad news for our claim. If you do not reject HO, if you can't knock out this guy, you cannot support the claim. So we're going to say, again, there is not sufficient evidence to support the claim, or conclude, you can use that word, that the proportion has changed since 2000, or P not equal to 0.58. You just restate the claim right there. Okay, so here's a couple follow-up questions. Are we supporting the claim? Well, what does this say? There's not enough evidence to support the claim. Are we supporting it? No. Did we find statistically significant? No. Everything's sad here, right? Everything's negative. Was the test statistic in the rejection region? No. Was the p-value smaller? No. Did we reject? No. There is not sufficient evidence. Do you see how everything has a negative connotation to it? So are we supporting the claim? No. And you're like, but it was different. I know, but it wasn't different enough. That's what we're testing here. It wasn't different enough.